Okay, I don't want to talk about it in class. There's still someone who hasn't taken it, but I'd be happy to go over it after. Um, so first of all, Tuesday is the first test. That would be the 4th. Um, and the topics are everything up through particle statics. So I'll start. If anybody has any questions related to the test, I'd be happy to answer as many homework questions as you have. Anybody want to go over anything? Yeah. Oh, yes, that's right. I didn't look that up before I came here, but what did I say? Up through number 10? What was, well, let me look and make sure. Let's get this right. Might have been dynamics. That's okay. Okay, let's look. Okay, yeah, those are all good. So everything up through particle statics. Okay. Yes. Yeah. Right. And well, statics doesn't really have too much for equations, but I'll always give you any equations you need to. Okay, so number 8. Um, so let's see, you have a ceiling. Anybody happen to have that problem? Okay, so you have a mass that's connected to these 2 hanging pulleys. And then there are 2 pulleys connected to the ceiling. And a cable connects to these pulleys like this. And all of those cables make angles of 60 degrees with the horizontal. So for each one of these, this angle is 60 degrees. And we want to calculate the force vector the cable applies to the wall, the cable tension, and then do it as the angle with the horizontal approaches 0. So the free body diagram I'm going to draw is all of the stuff that's hanging, all the stuff that would crash to the ground if that cable were taken away. So it's like that. The weight force is 100 times 9.81, so 981 newtons. And now the cable forces are all parallel to the cable, away from the body. So there's a force like this, a force like this, a force like this, and one like this. Those are the places where the outside world makes contact with the boundaries. And since those are all the same cable, just going through pulleys, these all have the same tension, the same magnitude. Okay. And so there are two vectors that we have to figure out the components for. So if this is our coordinate system, the cable force here, you see my cursor, and here are both this way, where this angle is 60. And the ones here and here are both this way, where this angle is 60. So to go from the positive x-axis counterclockwise to the vector on the right, the first one I drew, is just 60 degrees. And from the x-axis to the other one, you can think of it as go all the way 180 and then backtrack 60. So this is 120. And so Newton's second law says 0, negative 981, plus t times cosine and sine of 120. So that is negative 0.5 t, positive 0.866 t. And there's two of those. And then there's two of the ones at 60 degrees, so that's plus positive 0.5 t, 0.866 t, and another one of those. And all these add up to 0. So you get two equations. The first one, though, notice that these, the two negative 0.5 t's and the two positive 0.5 t's cancel each other. So these all go away, and you get an x equation that just says 0 equals 0, so you can't use that. But the second one says 4 times 0.866 t is equal to 981. And that is 3 3.464. T is equal to 981. And so T is equal to, what's 981 divided by 3.464? 254.33 newtons. And if you compare that to the one where those cables are all vertical, well, that would have been 981 divided by 4. So this is a little bit bigger. Did I do that right? Okay. $283.19. Well, so anyways, it's bigger than when they're hanging vertically. And so now what happens if that angle goes to 0? Well, there's sort of a sloppy way to do it and a careful way to do it. The careful way to do it, I suppose, would be to do this for some angle theta and then take the limit as theta goes to 0. But the answer is that cable tension goes to infinity as these, as this lifts up. Those are all in line, so that cable is just going straight across. That cable tension would have to approach infinity. Basically, because there's no vertical components of that cable force to counteract the weight, if it's all going horizontal. Any questions about that one? Any other homework problems you want to see? Oh, okay. So it asks for the vector that the cable applies to the wall. Okay. So if this is also 60 degrees, then theta for that is 120 degrees, and you'd go 283.19 times cosine and sine of 120. Yeah. Yeah, sure. So if you're talking about the force that cable applies to the wall, a cable force is always parallel to the cable away from the body. So that force is going to be this way, right? And so it's represented by this direction. So the angle is 120. So it would be 283.19 times cosine and sine of 120. Any other questions? Yeah. Yeah. Well, as that angle that's 60 degrees in this picture goes to 0 degrees, so the thing approaches being horizontal, the cable tension approaches infinity. And as it gets closer and closer to 90 degrees, well, that one you don't have to do as a limit. When it's hanging exactly at 90 degrees, it's 981 divided by 4. So I guess that's, who knows, impossible to calculate. No, it's probably 24.525, 245.25. Any other homework questions? All right, so now we're going back to moments in rigid body statics. And the way you calculate a moment is, so the moment about some point A is the row vector crossed with the force vector. So this is the moment produced by that force F, where rho is the vector to the point P where the force is applied from the about point, and F is the force vector. There's one thing that I want you to have intuition about, the direction of this moment. So notice that a moment is always a vector. Okay, sometimes, and so a vector has a magnitude and a direction. And we'll sometimes use simplifications where we treat it like it's a scalar, but it's always a vector. So I want you to have in mind what the direction is. So remember, I gave this example that I think is sort of a nice way to picture what a moment does, where you're trying to turn this bolt by turning a wrench, by applying a force to this wrench. And if you apply a force this way, it's going to rotate it counterclockwise. So this is the force, this is the point P where the force is applied, not rho, P. Okay, this is the about point. The rho vector goes from A to P. Okay, so what's the direction of the moment? The direction of the moment is determined by the right-hand rule. So have your fingers curl in the direction that the object is going to rotate, and your thumb points in the direction of the moment. Okay, so the moment is going to make it rotate counterclockwise, fingers go counterclockwise, and your thumb comes out. When we're doing problems in the plane, when we're doing two-dimensional problems in the XY plane, the moments are always going to be either positive z, or if it's a moment the other way, negative z. Okay? And so a lot of times when you're doing plane problems, people treat moments like they're scalars, because all you really need to represent the direction is a positive or a negative. But you have to remember that it really is a vector, and that vector is always perpendicular to both the rho vector and the force. Okay. So notice for 2D problems, moments are always, and for 2D, like when I do 2D, I'm always going to use the XY plane. Moments are always parallel to the z-axis. Okay, why is that? Well, if you take, so let's say we have a moment that we're calculating between a row vector. So let's say our row vector is row x, row y, 0. Okay, so that's a vector that's in the xy plane. And we're crossing that with a force vector that's also in the xy plane. The answer is 0 for x, 0 for y, and then rho x fy minus rho y fx. Okay, so if rho and f are both in the xy plane, the only non-zero component you can get for your moment is z. All right, well, let me do a two-dimensional example. Let's say we have this board, and it has a width of 0.5 meters. And a length of 2 meters. And let's say that there is a force applied here straight up of 20,000 newtons. And a force applied here straight to the right of 10,000 newtons. And let's take two different points. Let's say that there is a point A here and a point B here. And we want to calculate the net moment. So that's the sum of all the moments first about the point A, and then we'll do it about the point B. And what we're going to see is that the moments depend on your about point. Okay, if you choose a different about point, your moments are going to come out different. Yeah. Okay, so before you calculate moments, you should draw a free body diagram, but this is already a free body diagram. All we have is forces. So I'm going to go straight to, remember I said that I think it's a good idea for bookkeeping to write out a table for each rigid body you do. So we'll have a column for the row vectors. This is part A. A column for the force vectors, and then a column for the moments. And then we'll have two rows, one for the 20,000 Newton force and one for the 10,000. So first I'll do the 20,000. And I'm using the usual coordinate system. Okay, so if our about point is A, what's the vector from the about point to the point where the 20,000 Newton force is applied? So from A to where that 20,000. Well, you have to go, so if you start here, you can think about it as just a set of directions to get there. Start at A, go 2 meters in the positive x direction, 0, 0. Everybody with me on that? And then what's the 20,000 Newton force vector as components? That's in the positive y, so 0, positive 20,000, 0. And now take the cross product. You get 0 for x, 0 for y. This is a plane problem, so it always has to work out like that. And then the z component is 40,000. And now we'll do the 10,000 Newton force. So for the 10,000 Newton force, we're going to start at A, and we need to come up with a row vector to get from A to where that force is applied. So for that one, you go 2 meters in the positive x direction, and then half a meter in the negative y direction. So it's 2, negative 0.50. The force vector is in the positive x direction, so it's just going to be 10,000, 0, 0. And for this one, again, you get 0, 0. And then the z component is 2 times 0 minus negative 0.5 times 10,000. So that's a positive 5,000. And so the net moment, the sum of the moments, I'm supposed to say net, is 0, 0, 40,000 plus 0, 0, 5,000 so that's 0, 0, 45,000. And if this is all in newtons and meters, then the units are Newton meters. If this wasn't, if these were the only loads acting on it, then the sum of the moments would be in the positive z direction, which means that this thing would have an angular acceleration. Would it be a clockwise angular acceleration or counterclockwise? Counter, yep. So a positive z component is counterclockwise. A negative z component is clockwise. It's the right-hand rule. Okay. So now I'm going to do the same thing, but with a different about point. So we were first doing it with the about point at A. Now we're going to do it at B. Is it going to be the same answer or different? I don't know, but it's going to be different in general, unless I pick my numbers badly. So what I want you to remember about this is your about point is part of the answers that you get for this. If you choose a different about point, you get different answers, okay? We'll, in this class, be able to choose any about point we want, but I I want you to remember that the about point is part of determining what the moment is generally for a force. Okay, so I'm going to write out the table again. Row vector, force vector, moment vector. And I'll start with the 20,000 again. Okay, so this time our about point is B. So a row vector starts at B and goes to where the force is applied. So that's a positive 2 for X, and then a positive 0.5 for Y. So 2.50. And then the force vector, that doesn't change from before. That's still 0, 20,000, 0. And so the moment, if you take that cross product, is 0, 0, positive 40,000. Yep. And now we'll do the 10,000 Newton force. What's the row vector for the 10,000 Newton force? Let's start at B. And we just go 2 meters with the positive X. So just 2 zeros per out. And the force vector is 10,000, 0, 0. But now, before we calculate this, just look at this picture. So the way you can always think about this is if the about point is like a frictionless hinge, and the only force acting is the one you're looking at that instant, would that force make it rotate or not? So think about this. If I had a hinge right here, and the only force you were applying was straight away from the hinge, would that make it rotate? No. And so we expect this to produce no moment. Okay. And the cross product does that. So we have 0 for X, 0 for Y, like we always do in the plane. But 2 times 0 minus 0 times 10,000 gives us another 0. And so for this one, the net moment about, I guess it's B this time. I'm going to change these subscripts to B's. Then it's just 0, 0, 40,000 plus 0, 0, 0. So Newton meters. Yep. Yeah. Sure. Okay, let's do, any other questions about that example? Yep. So rho has units of length, F has units of force, and so in SI units, it's always Newton meters. Okay, let me do a 3-dimensional example. So let's say we have this plate. And at the center here, I'm going to draw the coordinate system we're going to use. So let's make the x-axis go that way, the y-axis go up, and the z-axis to the side. And let's say that at that origin, there's a cable connected that goes directly to the wall right above the corner there. So this cable goes like this. And this distance is 1 meter. And then the size of this plate is 2 meters in both dimensions. So 2 meters that way, 2 meters that way. So now if we assume that the cable tension is 10,000 newtons, what's the moment produced by the cable, or what's the moment, this vector MA, applied to the plate by the cable? And we need to specify an about point, and the one I'm going to use is this right here. Okay, so the force applied to this plate is going to be parallel with that cable, away from the body, so away from the plate, so pointing that way. And we're going to calculate the row vector and force vector, and then just do the cross product. So we'll set up the table the same way, but it just gets, you know, in 3D, there's more stuff to think about. Okay, so first let's figure out the force vector. What process are we going to follow to come up with that force vector? We know that the magnitude is 10,000 newtons. Yeah, so you could do it with cosine and sine, but when I mentioned the different ways to come up with the unit vector, I said that you probably don't want to ever use the angles and cosines and sines in a 3D problem. It's probably only useful in 2D. So instead, if we could come up with, so let's come up with a vector that goes from this point to this point, and then we'll normalize it, okay? Divided by its magnitude. Okay, so what's a vector that, or it's not from here, sorry, it's from the above, no it is. Okay. This is the real. So we want a force, we want a unit vector that goes from this point to here because that's the direction of the cable. Okay. So to go from here to here, we won't worry about a unit vector yet, we just want a vector. So how do you do that? You can go, yeah, 1 meter along the negative x-axis, and then you can go 1 meter along the positive z-axis, and then 1 meter in the positive y, along positive y. Okay? You with me on that? So here's the path I'm gonna take. I'm gonna go 1 meter that way. That's negative x. Then I'm gonna go 1 meter that way. That's positive z. And then I'm gonna go 1 meter that way. So this vector u that's in the direction of that cable force is -1 for x, +1 for z, and +1 for y. Now we want to make it, we want to normalize it, we want a unit vector in that direction. So we need the magnitude of this vector, and that's -1 squared plus 1 squared plus 1 squared square root. So that's √3. And now the unit vector that we want is, -1 over √3, +1 over √3, +1 over √3, which I think I remember is 0.577, something like that. So we have -0.577, +0.577, +0.577. Okay, so that's a unit vector in the direction we want. Yes?
Did we only not normalize the force vectors for the 2D problem?
We already knew what those, well, in a way we did. So what you can think of, what we did is we thought of, so we knew the magnitude was 10,000. We thought of the unit vector in this direction, which would be 1, 0, 0, and then multiply it by 10,000. But when they're just along the axis directions, it's pretty easy to do in your head. We just knew it was in the positive x, and that's all. But yeah, you could still think of, like, this has the unit vector 1, 0, 0. This has the unit vector 0, 1, 0. And then we're just multiplying it by the magnitude we use it all in our head.
So we're going to multiply that.
Yeah, now we are. Yep. So now we have this unit vector. So the force vector is 10,000 times that. So -577, +577. What comes after the 7th? Okay. So let's just make that 4, 7, 7, 4, 5, 7, 7, 4. Okay. Any questions about that? And now the next thing we need is a row vector. And the row vector goes from the about point to where the force is applied. This is the about point. So we need a vector that goes from here to the place that that cable applies the force to the plate is there. Okay. So we can think of that as going 1 meter to negative x, 1 meter to positive z, and then we're there. Okay. So that row vector is -1, 0, 1. The way, so a meter this way, and then a meter this way. And so now I'm going to set up the table, even though there's only one force and one moment here, I'm just going to set it up. So row vector, force vector, moment about A. So the row vector is -1, 0, 1. The force is -5, 7, 7, 4, +5, 7, 7, 4, +5, 7, 7, 4. And now the cross product, you have -5, 7, 7, 4. Just plug it into your calculator to do this. Then this comes out to be 0, I think. So -5774 plus 5774. And then the last one is -5774. So that cable applies a force about A of -5774, 0, -5774, and the units are Newton meters. And so it's producing a clockwise, clockwise rotation or clockwise moment about the x-axis, clockwise moment about the z-axis, nothing about the y-axis. Any questions about that? What if I chose a different about point? Would I get the same answer or a different answer? Different answer. Okay, so now the next thing that I want to talk about is the one case where moments don't depend on the about point, okay? And that is called the moment of a couple. People normally just call it a couple. But really what we're calculating is the moment produced by a couple. And a couple is two equal and opposite forces acting at a distance. For example, if you've ever seen any kind of bolt that you turn with like a spanner tool, old bikes, you used to have to do this all the time. So you put one little notch in there, one thing in there, and then you turn it by, when you turn the spanner, it applies a downward force there and an upward force there. They're equal and opposite forces. So if that force is the opposite direction and the same magnitude as that other one, that's a couple. And what we're going to see is that for a couple, couple produces a moment that doesn't depend on the about point. It's the same no matter what the about point is. So you can think of a couple as like just a pure moment, okay? No matter what your about point is, you can just add this pure moment onto the rest of your moments. Okay, so that's surprising. It's the only thing that does that. And it's an explanation for why we're going to treat couples the way they are when they, what a couple really is these equal and opposite forces, but we're always going to just treat it like you're adding on a moment of 400 Newton meters or something. Okay, you're just adding on this number. Where does it come from? And so where it comes from is the two equal and opposite forces, but that nature makes it so you can treat it like just this couple of its own. Okay, so let me show this. Don't believe me? Prove it, thank you. So here's just some arbitrary body. And here's some about point. And we'll apply a force F I'll call, just F. I'll apply that at a point P1. And then somewhere else on the body, I'll apply an equal and opposite force. So those are parallel, but it's going the other direction. That's also F. And the point where that force is applied is P2. And just to be careful with the notation, so those magnitudes are the same, but if you're representing this in components, that vector I'm going to call negative F. Okay. All right, so we're going to calculate the sum of the moment produced by F and the moment produced by negative F. Okay. So the row vector for F goes from the about point to here, right? That's I'll call that row 1. And the row vector for the negative F force is like this. I'll call that row 2. And what do we expect to happen? So I'm going to set this up as, the total moment of this couple is equal to row 1 crossed with F plus row 2 crossed with negative F. And what would show that this moment is going to be the same no matter what the about point is? How would we see that in this proof? Well, we haven't seen it yet, but what are we looking for to prove that it doesn't depend on where A is? What we're going to see is that the value for A, the components of A, are just going to disappear from the calculation. Okay, so like to start with, they're in there. This row 1, we can write this as P1 minus A crossed with F plus the quantity P2 minus A crossed with negative F. Okay, so they're in there. If you, like looking at it right now, change the value of A, change where that about point is, the coordinates of that about point, looks like it'll change the answer. What we're going to see is that those cancel out. A isn't in there at all. So it doesn't matter what the numerical value of A is. Okay. Does that make sense that that would show us that it doesn't depend on that A? Okay, so you can distribute multiplication out with the cross product. So this gives you P1 cross A, P1 cross F minus A cross F. That's the first one. And then add on the second one that says P2 crossed with negative F minus A crossed with negative F. And now you can pull out the negatives. So P1 cross F minus A cross F minus P2 cross F plus A cross F. And now you can see where that cancellation happens. And so what you get is the cross product of this difference, P1 minus P2, and F. So what we saw is that the moment of a couple is the same no matter what A is. So when we see couples and problems, we're just going to represent them as a moment, because if a couple produces a moment of 450 Newton meters, then no matter what you choose as your about point, that's what it's going to be. So we'll just put it on there as just a moment and nothing else. It doesn't produce any force. You don't have to worry about the forces because they're equal and opposite. They cancel out. Okay. So the way we'll represent, so the representation of couples in 2D will usually be like this. Or this. Okay, so that's saying clockwise or counterclockwise. But remember, a moment is really a vector. So even though it's shown like this, that would really be a vector in the positive z direction. This would be a vector in the negative z direction. And in 3D, these will be represented as vector components with double heads. So you'll see stuff like this. Heads for the two forces, I guess. And you won't always have all three. So if you see something like one like that, and one like that. That says that there's a couple in this direction and this direction, but not one in that particular direction. That can only be zero. Any questions about that? Okay, so let me do one quick problem. Oh, it's not that quick. I'll do this next Thursday. Okay, so test on Tuesday, and then we'll get back to this on Thursday.